boys and girls, children of all ages, presenting the 20th Anniversary Annual Holiday Lecture, University of Wisconsin Chemistry Professor Bassam Shakhashiri.
Thank you, and good evening, everyone, and welcome to my lab. I promise you a very good time tonight. I want you to be as attentive as possible. It's so nice to see so many old friends and to make some new friends tonight. These are very special days for all of us because it is the holiday season and because all of us are eager to learn about different things that surround us. We're all curious about the world that we live in, and we're going to do a number of scientific experiments tonight. I hope you will find them enjoyable and rewarding. I want you to know that this is the 20th anniversary of this special lecture, and I'm so proud to have had the opportunity and the privilege to be a faculty member at the University of Wisconsin-Madison for that length of time. I want you also to sit back and relax and enjoy what's about to happen. I want all of you to pay special attention for color changes, be on the lookout for smoke that might come out, and maybe an explosion or two that might happen. As we do experiments, we want to be obeying all the safety regulations, and you will see that I will put my eye goggles, eye protection on, the safety goggles, to protect my eyes from possible splashes that might take place. I also want you to see that we have a fire extinguisher available just in case something does go out of control. We're not planning on anything going out of control, but we have to be very careful as we do the experiments tonight. Now, why do experiments in chemistry? Why be concerned about chemicals? Because chemicals are all around us. The food that we eat is made up of chemicals. The air that we breathe is a mixture of chemicals. The clothes that we wear are made up of chemicals. Our own bodies are made up of chemicals. What goes on inside our bodies is nothing but a series of biochemical reactions. The medicine that we take when we are ill is nothing but chemicals. The drugs that some of you foolishly experiment with are also chemicals. And that's why we need to be concerned about the properties of all chemicals, their benefits, their potential hazards, and of course we need to be handling them in a very safe manner. And that's why we want to now go through a series of experiments that show us that we are having a lot of fun. You know, my button says here, science is fun. Fun in the best sense of the word. And that's what I would like you to have with me tonight also when you go back home and do some of the experiments that you might be able to perform at home, to have fun and to be challenged and to be enjoying the festivities that are about to take place. Now, because I'm going to do a lot of different experiments, it would be easier for me if I took my jacket off. Would that be all right if I took my jacket off? That'd be all right? Okay, so let me do that then. And I'll put my jacket over here. How about if I took my tie off too? Would that be all right? All right. It makes life easier for me if I take my tie and loosen my collar a little bit. We can put this away here. How about if I take my shirt off? Will that be all right? Okay, let's try that. And I want you to see that I really believe that science is fun, and that's why I'm wearing this T-shirt that gives that message too. So I'll get the microphone back up here, and we'll start the experiment by doing a simple reaction we call a combustion reaction. We take a match and we strike it. Lots of exciting and interesting things happen here. For one thing, this reaction releases energy in the form of light, that's what we see, but also releases energy in the form of heat. Because you know, if I don't blow this out right now, I'll burn my fingers. How do you know that? You know that from experience. And that's a key word I want you to be thinking about and using. Use the experience that you have to learn more about the chemical world that we live in. So that is one experiment that we will do. And I want to now show you a very special experiment. I'm going to take a dollar bill, and I'm going to strike a match and very quickly burn this dollar bill. Did you see that, or was that too fast? See, what we do in science, we try to repeat the experiment to make sure that the observations are valid. And so what we have here is what looks like a dollar bill. It's not a real dollar bill. This is made of special paper. This paper is treated chemically so that when it burns, it does not leave a residue. And that's what I'm going to try to show you again. Take this and watch what happens. There it goes. Okay? So if you know chemistry, if you know science, you can do a whole bunch of different experiments. And that's one other experiment I'm going to try to do now. I'm going to take a $20 bill. After all, this is the 20th anniversary, right? But take this $20 bill, put it in this empty beaker, like so, and add a liquid to it, just to soak it up. And what we'll do next, take this $20 bill, soak it real well in this liquid. What does this liquid look like? It looks like water, but actually it's not water. It is a mixture of two liquids. One of them is water. So what we'll do next is take the match, strike it, and see if we can burn this $20 bill. And you saw the flame? But the $20 bill is still intact. That's because this mixture is made up of water. As you know, water does not burn. In fact, you use water to put out fires. But also another chemical. Its name is isopropyl alcohol. And this mixture causes the effect that we saw to happen. The alcohol burns, but the water does not burn. And so this $20 bill is still good. I'll put it back in my wallet, and I will use it to get some Christmas presents. All right, so that's one example for us in terms of combustion. There are substances that burn and other substances that do not burn. Those substances that burn are called combustible substances, and what we're going to do now is try to use this big torch that's connected to a fuel called methane. We're going to try to strike a match and see there. This is an example of a controlled combustion reaction. This gas that's burning is called methane. It's natural gas. It's used as a fuel to provide us with heat. It's used to heat this building, to heat our schools, to heat our homes. That's because the combustion of methane is an exothermic reaction. That's a reaction that releases heat, that releases energy in the form of heat. It also releases energy in the form of light, as you see the flame. If you look very closely, you see that the flame is mostly yellow, but has a blue tinge near the tip of the burner. And one of the things that we study in science is to try to understand why different flames have different shapes and different colors. Well, when you came into the auditorium this evening, you noticed a whole set of different things on the lecture table, and also you saw these balloons. And I want to ask you, what do you think we have in those balloons? Helium, you're saying? Some of you are saying helium. Well, let's set this aside for a moment and ask you, why are you saying helium? Remember what I asked you to think about before? I asked you to use the word experience. You are saying helium because you know from experience that helium-filled balloons are lighter than air, and they must be kept on a string, otherwise they'll go up to the top of the room, or if you're outdoors, they'll just go up in the air. So the other thing we want to talk about and deal with tonight is that helium itself does not burn. It's a non-combustible gas. So one way in which we can find out what is in those balloons is to take this flame and try to see if the balloons burn. All right, so we'll take this flame and put it to this balloon. And what happened? The balloon popped, right? The balloon popped, and I can tell you that that balloon, the green-filled balloon, had helium in it, and helium is a non-combustible gas. So we go to the next one over here, and we'll see if this one has helium in it or not. Now that balloon exploded when we put the torch to it. That balloon was filled with hydrogen gas, and hydrogen gas combines with the oxygen that's in the atmosphere in a very explosive manner, as you saw. So what we're going to do next is repeat the same experiment with the second yellow balloon, but do it in the dark and see if we can make some additional observations about the color and the shape of the flame. You ready? Here we go. Now with the lights on, I'm sure you noticed that the flame itself was big and had a special color to it, and there was also sound energy released in that explosive reaction. What we'd like to do now is to show you this last experiment in slow motion. So all you have to do is watch the monitor, and you will see the experiment. Again, you won't hear any sound. There's the flame coming to the balloon, and pretty soon you'll see a big ball of fire. See, that tells us then, if we study that, we can study the behavior of that explosive reaction and learn something about combustion processes, especially the combustion of hydrogen. Now, you being very good observers and making sense out of what we're doing here, you notice that when we went from the green balloon to the yellow balloon, the amount of sound energy increased, right? Got to be higher. So as we go to the red balloons, you might guess that there may be more sound energy. You might guess there may be the same or even less. But remember, we said we want to be obeying the safety regulations, and therefore we should be protecting our eardrums from potential damage. And the way to do that is for you to take both fingers like so and put them in your ears. Okay? Now, if I were to do that, I can't do the experiment. So what I have brought along with me are some earplugs, and I will put the earplugs, and you put your fingers very, very strongly in there. If you can hear what I'm saying, that means you don't have your ears plugged in safely. I can't hear you, but I can see you laughing. So make sure that you have your ears protected, and we'll do this and see what happens. Now, that balloon had in it a mixture of hydrogen and oxygen. So the oxygen was in immediate contact with the hydrogen, and that's why the amount of sound energy was much, much higher than before. Let's repeat that experiment in the dark now, okay? So plug your ears very well. You notice that the shape of the flame and the color of the flame is different, right? In fact, what we should do now is take a look in slow motion at this last explosion. Again, you won't hear any sound. you'll just see the ball of fire. There comes the flame, and very soon, there you go. Well, that is an example of a combustion reaction that goes out of control. And that's why we need to keep flames in any source of ignition away from hydrogen and from mixtures of hydrogen and oxygen. So what we're going to do next now is try another experiment in these plastic bottles that have two nails stuck on the side, and they are separated on the inside by a distance of about 1 centimeter. You know, in science we use the metric system, not the British system, for measurements, and so the distance is in centimeters. And there's a cork at the top, and then there's a small amount of liquid at the bottom. And what we're going to do is use this sparker. I'll show you, there's a big spark coming out of this. I hold this very tightly. There, you see the spark? Okay. We'll try to spark this and see what happens. That is another example of an uncontrolled combustion reaction. The liquid that's at the bottom of the bottle is ethyl alcohol, and the vapor from the ethyl alcohol is ignited when the spark jumps between one nail and the other nail. So we have a whole bunch of these, and let's try to do them. All right? You ready? Okay. We'll do another one like so. There you go. You see what happens, that chemical energy changes into mechanical energy, and the cork is ejected. All right, here's one more. There you go. You notice again that the sound energy that's released depends on the size of the container. Let's try this next one in the dark and see what happens as we try it in the dark. You ready? Okay. Now I can't see what we're doing. Whoops. Let's try it. Here we go. There. Okay, now I want you to know also that as I touch these bottles that they feel warm. Not this one. Nothing happened with this one. Oh, I can tell you why nothing happened here, because the two nails are touching. So we need to separate the nails. But we've had enough of these explosive reactions, right? All right, so let's move on to something different and something that relates to combustion. If you take a balloon, you know I like balloons, and you blow the balloon up like so, then you can tie it. And because it's filled with air, right, it's not going to rise. It's going to sit like so. Now, if you take a match and you strike this match, right, and you hold the balloon up like so, and you put the match, oops, the balloon pops, right? You know that. Now, here's an experiment that you can try doing at home. You take a balloon and you put in it some water before you blow up the balloon. Fill it up with water. Okay? And I have a small funnel here just to help me get the water in. But it makes it more difficult to get the balloon off the funnel now. All right? And the next thing that you do, whoops, is you blow. About this size. You tie it off. And you have this water in the balloon, right? So you put this off like so. You get a match, and very carefully, you put the match right where the water is. Whoops. I held it too long. If you do this carefully and don't hold the match too long close to the balloon will not pop. Now you try this experiment at home. Make sure when you try this experiment that you do it with an adult, because anytime you play with matches or with fire, it is a very dangerous situation, potentially very dangerous, and that's why you need to be very, very careful about it and do it with an adult. Now, let's move on and talk about and do experiments with one of the products of the combustion reaction, especially if, not especially only if, the material that's burning contains carbon. Carbon-containing materials produce, in a combustion reaction, produce carbon dioxide. And what we're going to do next is do a whole bunch of experiments with carbon dioxide, which is at room temperature and pressure a gas. Except that, in this case, we're going to use carbon dioxide not in the gaseous form, but in the form of a solid. And what I have here is chunks of dry ice. These chunks of dry ice are solid carbon dioxide. And solid carbon dioxide is at a temperature of minus 78 degrees Celsius. Again, we use the Celsius scale when we measure temperatures in science. This solid carbon dioxide does not change from a solid to a liquid to a gas. It changes directly from being a solid to being a gas. That process we call sublimation. So it's at minus 78 degrees Celsius, and it sublimes. It goes up directly from being a solid into a gas. And so unlike ordinary ice, if you put ordinary ice in a glass, what happens? It melts, right? And then after it melts, it disappears because it changes into water vapor. This carbon dioxide in the solid form does not change into a liquid. It goes directly into being a gas. And what we're going to do next is carry out a whole bunch of experiments with carbon dioxide in the solid form to tell you for sure that if you take carbon dioxide and you put it in water, you get carbonated water. In fact, all carbonated beverages have in them carbon dioxide gas that has dissolved. So what we're going to do now is take chunks of carbon dioxide, of dry ice that is, and we're going to do a whole bunch of experiments with these tall glass cylinders that are arranged in a very special order. See, we have a pair of one color, another pair of a different color, a third pair of still a different color, and a fourth pair of a color that's very close to the color of the first pair. What we're going to do is take chunks of dry ice and drop them into this cylinder and into this one, and we see what happens. Lots of interesting things begin to happen. Put a little more here, and you see bubbles. That's the carbon dioxide bubbling, and you see some color changes taking place. Remember, I told you to be on the lookout for color changes, and I also told you to be on the lookout for a lot of interesting things that might be happening. You see this white stuff coming off the top here? What do you think this white stuff is? What does it look like? No, it's not carbon dioxide. Carbon dioxide is an invisible gas. You can't see carbon dioxide. What does it really look like? It looks water vapor. No, water vapor is also an invisible gas. It looks like fog, as someone said. You know what fog is? It's condensed water vapor. And the condensation is taking place on the carbon dioxide that's escaping. So we can look at this. Isn't that interesting here? Now, one of the things that we do in science is pay close attention to all kinds of changes, including color changes, including the release of the gas and the condensation of water vapor in this case. Now, these are all at room temperature, and what I want to show you next is an experiment where I will take an empty dishpan like this, put it over here, and I will put in it some hot water, some boiling water, and then we'll put some dry ice in that and see what happens. So I'm looking for the hot water. I need a flask of hot water. I guess it's not here. Can someone bring it out to me? Oh, come on over. Oh. Thank you, Bucky, and welcome. Welcome, Bucky. Bucky is a very special chemistry student. He's been taking chemistry every year ever since I've been here. And he actually likes chemistry. Don't you like it, Bucky? Yeah, good, good. I want to thank you for being here tonight, Bucky, and for helping out with this special 20th anniversary of this presentation. I'm very, very happy that you're here. And I want to do the experiment that I talked about here. So Bucky, if you would watch as we put the water in this dishpan. What do you see coming off the top here? No, steam is an invisible gas. You can't see steam. What do you see? No, water vapor is invisible too. What is it? Condensed water vapor. That's what it is, okay? Bucky, you got that, right? So let's take some dry ice and put it into this. Now what does it look like? And you see that it is moving in a downward direction. That's because carbon dioxide is heavier than air, and the condensation is taking place on the carbon dioxide. You see that, Bucky? Now, initially, at the beginning of this experiment, the fog went upward. So you want to think about that. How come initially it went upward, and now it's going downward? Remember that this was hot, boiling water. So that's a little hint for those of you who want to think about it. Now, Bucky, I know you're getting ready for final exams and you probably want to study, but I wonder if you can stay for the rest of this set of experiments. Can you? Do you want Bucky to stay? All right. Well, I have a special place for you, Bucky, right here. If you have a seat right here, you can watch all the experiments and see. Are you comfortable, Bucky? Great. All right. All right. So let's move on and look. Did you bump your head, Bucky? Do you need any first aid? You're all set. Okay, great. All right. Let's move on and do a couple of other experiments that deal with carbon dioxide and show you one of the experiments that involves a candle before we get to the carbon dioxide. You know, the great British scientist Michael Faraday started the tradition of the Christmas lecture by talking and demonstrating the chemistry of the candle. Now, you ever wonder why the candle stays lit? Why does the candle stay lit? You think about that and think about the flow of the fuel, which in this case is wax, through the what? What's inside the candle? Through the wick, right? Into this area where there's a lot of air, and air is 20% oxygen, so combustion is taking place right there. So think about that as we do the following experiment. This experiment, where I have placed some dry ice into this beaker before we started, and so the entire beaker now is full of carbon dioxide gas. And what we're going to do is pour some carbon dioxide gas onto the flame. Again, showing that carbon dioxide is heavier than air. It moves downward, and showing that it does not support combustion. So let's do this one more time and see. There's the candle, and we take the carbon dioxide and we pour it down, and you see again the flame goes out, showing us that carbon dioxide does not support combustion. That's why fire extinguishers are filled, one kind of them are filled with carbon dioxide. They're called carbon dioxide or CO2 fire extinguishers. And that demonstrates once again that carbon dioxide does not support combustion. So what we'll do next is go through a series of experiments that involve carbon dioxide in the solid form, that is dry ice. I'll put my gloves back on. Uh-oh, I hear some sound coming from someplace. Uh-oh.
Merry Christmas! Ho, 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 ho! Merry Christmas! Ho, 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 ho! Merry Christmas! Ho, 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 ho! Merry
Merry Christmas to you, Santa. How are you this evening?
Very good. How are you?
I'm doing fine now that you're here. I sent you a long list of things that I wanted for Christmas. I hope I was good enough that you brought them for me.
Oh, you've been a very good boy this year. Very good boy.
I'm glad to hear that.
Santa's brought you lots of presents this year for all the boys.
Oh, my goodness. Can I look in there?
Sure. Go ahead and take a look.
Is it safe to look in there?
Sure.
I got my goggles on.
Very good.
All right. Oh, my goodness. What do I have here? What do we have here? Oh, looks like a poster. Oh, my goodness. Here's a poster.
Oh.
This is a commemorative poster for this 20th anniversary lecture. Is this the only one you brought?
No, everyone gets a poster.
Oh, everybody will get a poster. Oh, that's tremendous. That's tremendous. Okay? And what do we have here? Another bag of goodies. Oh, my goodness. There is a what is, oh, it looks like a button. It is a button. So, did you bring one for everybody?
Everyone gets a button.
You mean? Well, you and your elves must have been very, very busy putting all of these things together. There are a whole bunch of other goodies in here. Here's a set of instructions for doing experiments at home. Let's see, there's 1, 2, 3, 4, maybe about a dozen different sets of instructions for doing experiments at home. That's very good. Very good. And other things that are in here, we'll just be sure that everybody gets a copy. I mean, not a copy, gets a bag as they leave, and a copy of this poster as they leave. And you and your elves have been very, very kind to me. I appreciate it.
Merry Christmas.
How's Santa? Can you stay?
Sure,
All right. We have a place for you. Well, 2 of my best friends are here tonight. I'm really proud of that. And I want to show you both another experiment that we will do with carbon dioxide. We take a whole bunch of dry ice and we put it inside what this looks like a fish tank. It's not really a fish tank, but it looks, you can use a fish tank at home if you have one. You put this dry ice in there. And the idea, let me tell you what the idea is. The idea is that you generate carbon dioxide gas and fill this container with carbon dioxide gas. Now, at home, you don't have dry ice, so how can you generate carbon dioxide? What you do is you take a small dish like this, and you put into it some baking soda and some vinegar, right? And you put a little bit of the baking soda. How much is a little bit? Let's see. About that much. Cover the bottom. Okay? And then you take this and you put it inside the fish tank. Make sure there's no water in the fish tank, right? And then you take the vinegar and you pour vinegar on top, and you see it fizzes. That's because carbon dioxide is being released. You wait for about 3 or 4 minutes so that the whole container is saturated with carbon dioxide gas. And then what you do is you get some soap bubbles, and you know what happens when you blow soap bubbles, don't you? Lots of pretty colors are on the surface of the bubble, and they float, but if you are very careful in blowing the soap bubbles into this fish tank that has been saturated with carbon dioxide gas, we'll see what happens. You see, the soap bubble doesn't sink all the way to the bottom. It just floats in the carbon dioxide until it pops. You do this very gently, and you can see a lot of interesting things happening. Not only are the soap bubbles floating in the carbon dioxide, but they are also pretty in color, and they are changing size. And I think, if I'm not mistaken, that Santa and his elves have included the instructions for doing this experiment in the handouts that you brought. Is that right, Santa? Oh, great. Very good, very good. So that's one experiment that you can do at home if you generate the carbon dioxide from the baking soda and from vinegar. All right, so we'll try to do next is a set of experiments with some other household chemicals that you might have access to. We'll take this bucket of hot water out of the way. And what we'll do is get, what does this look like? Cabbage. What kind of cabbage is it? Red cabbage, right? So what we'll do is try to chop off some of the red cabbage. We'll do it this way. And you be very careful not to cut your fingers as you chop up the red cabbage. Next, cut them off the other way. And now you have some chopped red cabbage. What you need is a blender. And you take the chopped red cabbage, or some of it anyway. You put it in the blender. And the next thing that you do is, what's the next thing that you do? Add water, right? Cover this with water. And what do you do next? You put the cover on, right? Remember the safety regulations, right? And you push the button. And what has happened is that you've made yourself some red cabbage juice. Now this juice is not for drinking purposes. What you want to do is to separate the liquid from the chopped red cabbage, and you use a what to do that? You use a strainer, right? Okay. And so you've got yourself now the red cabbage juice down there. You have a lot of it, but to do the experiment you need more, so you add water. The color stays the same. See? And the next thing that you do is you take a whole bunch of beakers or glasses, plastic or otherwise, and you set them up like so with something to stir, and you put some of the red cabbage juice into each one of them, about the same amount. Do I have about the same amount so far?
Yeah.
Are they about even?
Yeah.
How about that? Is that better? Okay, the next thing that you do is you take the vinegar that we used over here and you add the vinegar to one of the beakers. And you see what happens is that now you have a way of telling whether certain household chemicals are acidic or basic. You can tell the pH of those different substances. Vinegar has in it acetic acid, so that is basic. The next thing that you try is what? Try some ammonia. And ammonia is basic, so you know the color in basic solution. Then you can try a whole bunch of different things. We'll try this one first. Is this going to be acidic or basic? It's a carbonated beverage, right? So it has in it carbon dioxide, so if we add some, its color is going to be on the acid side, all right? Then you can try other household items. Here's Tide. Is this going to be acidic or basic? Well, don't guess. It's a 50-50 guess, right? So you see its color is on the basic side. And you can try then milk of magnesia. You can try Vanish. You can try just about anything you want at home, provided two conditions are met. Number one, the material that you try has got to be soluble in water, it has to dissolve in water. And number two, its own color should not interfere with the color of the juice. So if you take a colored substance, for example, and try to test its acidity, that will give you a confusing result. That's why I used this soft drink and not the other kind of soft drink, okay? All right, so, and I also think, if I'm not mistaken, that Santa and his elves have put instructions for this experiment, right, Santa? Mm-hmm. Wonderful, wonderful. All right. So far, we've been dealing with acid-base behavior of different substances. And by the way, when you get done with this, all you have to do is rinse everything down the drain with a lot of water, because everything is water-soluble that we are dealing with here. Now what I'd like to show you, right next to Bucky, I have two pieces of white paper, what I'm going to do is spray those pieces of white paper with a colorless and clear liquid, and we'll see what happens. You ready, Bucky? Okay, we'll start with the bottom one first. You see that? What does it read? It says 20th Christmas lecture. That's because we used something we call an acid-base indicator, and we painted those letters and numbers, and then we sprayed it with a liquid, which is household ammonia, basically, that causes the color to change. Now, we have another one. We have another one that we're going to spray on top of the first one. We'll see what happens when we spray it. There you go. Okay. Once again, if you know chemistry, if you want to study chemistry, you get to the point where you know enough about it that you can do these different experiments and have fun with them. As I told you from the beginning, doing science is a lot of fun. So one other experiment we're going to do now, and ask Fred to come out and help with this experiment. This experiment will be done at this end of the table, and Fred will explain to you what he's doing.
We've done some experiments with carbon dioxide tonight, and it puts out fires. You know that, right? Because we've seen that happen. In this tube, I've got a chemical which is very similar to carbon dioxide. It's called carbon disulfide. And what we want to do is see if we can put out the fire of a match if we drop it down into this tube. So what I'm going to do, I'm going to move the fire extinguisher a little bit so I don't kick it over here. And I'm going to light a match, and then I'm going to drop it into the tube. Now this will behave better in the dark, so I've only got one tube, so we'll do it in the dark just once. Can everybody see the match? You can take the stopper off, and here we go. And it goes out. So that particular mixture of chemicals puts out a match just like the carbon dioxide did. But do you see something else happening here? Can you see a reddish color coming up here? It's orange? Okay, it's orange. That, one of the other chemicals that was in here is one of the chemicals that makes smog when it hits the oxygen in the air, and that's exactly what's happening in here right now. So I'm going to take this away before we gas anybody in the front row.
Take it to a safe place, Fred, and put it in a hood, I think, and that will be the safe way of handling it. So let's move on and do another experiment by asking you to look at these two beakers that have in them what looks like a green liquid, right? And what we'll do to this is, because, again, it is a very special time of the year, we'll add a clear and colorless liquid, and you see what we get is a pretty combination of Christmas-type colors. Again, if you know what you're doing in chemistry, you can produce a lot of pretty colors, and you can handle those chemicals safely, as we must do every time that we handle them. The next thing we want to try to do is to move over to this part of the lecture table, and where we have a very large beaker full of water. The volume of this beaker is 4 liters. Again, we make volume measurements in the metric system, and we use liters, not quarts or pints. Those of you who need some help in converting from the metric system to the British system and vice versa can ask your teachers and can ask your parents to help you with that conversion. So what we'll do is add a slightly yellowish liquid, and see, nothing much happens. Then we take a clear and colorless liquid, we add this, and you see a lot of interesting things begin to happen. We're mixing this. What does it look like? It looks like a tornado. That's why we call this the orange tornado experiment. See, it's kind of yellowish at the top, but then at the bottom it is a orange kind of a color. So that is then an example of how an insoluble substance that's not dissolving in the water forms down the middle of the vortex where the chemicals have been mixed. All right, we'll let that go for a while. By the way, if we add more of this liquid, see, it disappears. If you add more of this liquid, it comes back. If you add a lot of this. So, again, if you know what you're doing and you understand the different chemicals, their properties, their behavior, you can have a lot of fun doing experiments of this type. So the next experiment we want to try to do is one where I will put some disposable gloves on because I want to protect my hands from possible damage. And what I'll do is take a liquid out of this bottle and put into this 1 liter beaker. What does this liquid look like? Looks like syrup, but it's not syrup. Actually, it's a very poisonous liquid, and we should never eat it or bring it close to our mouth. We take another liquid from a different bottle and add this. What does this look like? It looks like syrup too, but it's a slightly different color. And what we learned tonight, I hope, is that chemical reactions don't happen unless you mix them very well. Sometimes they happen very, very fast, like as we saw in the explosions. Sometimes they don't happen as fast. You just have to stir them up and watch out for changes that might be happening. Now, wait a minute. This thing is going out of control. This is what we call polyurethane foam. Polyurethane foam is made by mixing these two chemicals, and it is a solid. It is a solid, and it's a rigid foam. It's used for insulation purposes. It's also used for making materials inside of airplanes, like seats and other things like that. And it has very good practical applications, but also it suffers because when it burns, if there's a plane crash or anything bad like that, and this catches on fire, it releases gases that are very poisonous and very unhealthy for us to work with. I want to show you that this has become very rigid. It's a solid. See? Okay, so let's move on. And by the way, this should not be touched by the hand. That's why I'm wearing these gloves until about 4 or 5 hours after the experiment, so that we don't get our hands hurt by this experiment. So we'll go on now and use another example of a substance that we call a polymer. This is a polymer called polyurethane foam, and what we have here is another polymer called what? This is styrofoam. It's actually polystyrene, and what we'll do with the polystyrene is take a colorless and clear liquid and add that to the cup and see what happens. Whoops. You see that the bottom fell off. The bottom fell off, and it looks like the polystyrene is dissolving in this liquid. This liquid is called acetone, and what we have here is polystyrene in the acetone. But what I want to show you is that if you take a whole bunch of styrofoam peanuts and try to add them there as fast as you can, that they also disappear. So that's what happens if you do chemistry and you know what you're doing. You can make certain things appear, as we did here, and make certain other things disappear. That's the fun, part of the fun of doing science and doing experiments the way that we have been doing them. So now we'll do one more experiment with polymers. I will take this liquid that looks green in color, and we take another beaker the same size, and we put in it a small amount of a white powder. See the white powder down there? And then very carefully we take the green liquid and we add it over here, like so. And then what we try to do is pour it back in. And of course, it doesn't come out. That's because this polymer that was in this small vial absorbs many times its volume water. So this was water with food coloring added to it to give us the special Christmas-like color. And the water gets absorbed in this and it becomes a gel. Now this happens to have also practical applications. In fact, in one of the important applications that it has is its use as the absorbing material in diapers. And the instructions that you'll find in your packet, I think Santa brought these along too. You did, Santa, right? That tell you how to do this experiment using the diapers that you have at home. All right, so let's make sure you use the clean diapers, though, all right? All right, now we'll go on and do a very special experiment where we mix a clear and colorless liquid in this large beaker. We add another clear and colorless liquid, and so far not very exciting things have happened. Right, then we turn the stirrer on, and we let this mix, and we add the third one, and what is happening there? Is there anything happening there? I don't see anything happening. How come I don't see anything happening? Because I'm not looking, you're right. So every time I look at it, it looks blue to me, right? There it is, blue. Shall I look at it now? Right now? Right this minute? You sure? Blue. Every time I look at it, it's blue. When do you want me to look at it? Right now? Right now? You sure? Right this second? Blue. Now this is an example of what we call a chemical oscillating reaction. And you're right, it changes colors. It's very pretty. It's one of many oscillating reactions. It's a fascinating system. Again, that's why we study chemistry. That's why we study science and try to do research to understand the behavior of these different types of substances. I want you to know that this oscillating reaction was discovered by two high school teachers in 1973. It's a fascinating system that we want to look at. All right. So let's move on now and do another experiment. This experiment we're going to do in this spiral arrangement that we have in front of us. I'm going to take a clear colored liquid and a clear and colorless liquid and mix them together. You know, a lot of people confuse the words clear and colorless. You can have a clear and colorless liquid like so, and you can have a clear and colored liquid like this one. So what we'll do is mix those two liquids in this spiral assembly. We'll do this in the dark, all right? So here comes both liquids. This is an example. With the lights on now, this is an example of what we call a chemiluminescence reaction. This is the release of energy in the form of light, not in the form of heat. If I touch this, it's at room temperature. This is very similar to a reaction that all of you know about. That is the firefly reaction. That is called bioluminescence. That's because there's an enzyme in that fly that causes the glow to take place. Now, there are other experiments that you can do with chemiluminescence. This is not the only example. This is called a light stick. And what you do is follow the instructions that are on the wrapper. And you bend it like so. And if you turn the lights off, you can see that we have a very pretty glowing light stick. And because it is the holiday season, we want to see if we can produce a different color. Isn't that neat? All right, with the lights on now, then, I will ask Santa if he and his elves have included this experiment in the bag. You did? Wonderful. That is wonderful that you've done that. What we're going to do now is show you how versatile chemists and scientists are, and we're going to have a special salute to the holiday season that we're in by asking Fred to bring some beakers out with pretty colors and asking him then to present his special salute.
These beakers have been set up with great care because, well, first of all, I've got alternating red and green because it's Christmas, and then you'll notice that the levels are all somewhat different. And this is really an experiment where you have to pay attention with your ears as well as with your eyes to see what's really going on and to make sense out of the reaction. So I have a stirring rod here because we always need stirring rods in chemistry, and here's what we're going to do with the stirring rod. Merry Christmas, folks.
Well, we thank Fred, and I want you to know, as we close this very special lecture, that those of you who would like your teachers to be doing some of these experiments can get the instructions for doing the experiments by looking at these books that have been published by the University of Wisconsin Press. It's called Chemical Demonstrations, a handbook for teachers of chemistry, and your teachers can do those experiments for you, especially if they have the books. Now, as a special salute to our very special guests, I want you to see that I have prepared very special ornaments for them. Here's one, and here's another one. And I want Bucky to have this one. I want Santa to have this one. And I want to thank you all for being my guests again in my lab tonight. This has been a very special occasion for me, marking the 20th anniversary. Thank you all. Merry Christmas and Happy Holidays.